Chapter 1.4 Operations on Sets. From a book called How to Prove It. We are given three different sets, A, B, and C. A consists of elements 1, 3, 12, and 35. B has elements of 3, 7, 12, and 20. And C is read as elements of X such that X is a prime number. The bar is equivalent as saying such that, and X is a prime number has to be true for that element to be in this set. We are asked to do three things. First of all, we need to list the elements of the following sets, and then answer, are any of these sets below disjoint from any of the others? And the third question is, are any of the sets below subsets of any others? In question A, we're given A intersect B. Intersection means that the resulting set will have only elements that are common in A and B, or it is defined as elements of A and elements of B. If we look at elements A and B, 3 and 12 are only elements that are common in between those two. So A intersection B equals to set of 3 and 12. Before we move on, let's list some elements that are in C, because the next one involves the set C. A prime number is a natural number greater than 1 that is not a product of two smaller natural numbers. Here's a list of prime numbers. In B, we're given A union B in the parentheses and a difference of C. We know PEMDAS, so we start with the parentheses. So A union B is all the elements in A plus elements in B. So we have 1, 3, 7, 12, 20, and 35. Now we do the difference. Whatever in A union B, subtract whatever in C. So that means we do not include prime numbers in our result. In C, we're given A union parentheses B difference C. Let's start with the parentheses. A union stays the same, and B difference C is going to give us a set of 12 and 20. And union, as we know, is all the elements in A in addition to 12 and 20. So I will have 1, 3, 12, 20, and 35. I don't have to write 12 two times because it's in both. Now if we go back, they asked us, are any of the sets below disjoint from any of the others? Disjoint means that given sets have no elements in common. Now if we look back at our sets that we got from A, B, and C, we see that 12 is common in all of them. So our answer is no, none of the sets are disjoint. And now the last question was, are any of the sets below subsets of any others? And actually, A and B are sets that are subsets of C. And I cannot say that A is a subset of B because 3 is not common between them. And if I draw the Venn diagram, we have a C that is the biggest set, and that includes A and B. But A and B have one element in common, so they intersect. And we are done. Let's do another problem, number 4. They're asking us to use Venn diagram to verify the following identities. Difference can also be said as minus. So the first one we have is A minus A intersect B. These oddly shaped circles represent sets. And here's my set A, and here's my set B. And in the parentheses, it says that they intersect. Intersection is represented as this yellow shaded space in between A and B. And in order to draw a difference, we need to start with A, so everything in A is included. But we need to subtract whatever is in parentheses. So A minus A intersect B is this purple shaded area. In other words, we do not include that yellow shaded space, which is only elements that are in common between A and B. And B is not included at all in the result. And if I erase it, you can see that only A is there, except the common elements between A and B. And the right side of that statement, which is A minus B, is exactly what that means. So they are equal to each other from the Venn diagram that we see. Question B. A union B intersect C is equal to A union B intersect with A union C. Let's start with B intersect C. It's similar to the question before. The intersection is represented as this yellow space, and A will be a union of B intersect union of C. So our answer is this shaded purple area. And if we look at on the right side, A union B intersect A union C. That is exactly the same as A union B intersect C. Law for logical connectives also apply with the set theory operations. That means we're using distributive law here. Distributive law sounds just like what it is. We will distribute A union for both B and C. And a connective in between those two will be intersection. To recap, let's review all the symbols that we just learned. To remember the symbol of intersection and union, you need to remember union is big U, and intersection is opposite of that, so it's upside down U. And we have element of symbol that looks like E because element of starts with E. And we have difference of sets. Difference of sets, it looks different than minus sign because we're talking about sets and their elements. And we learned about such that, which used in set notations, and it represents that whatever comes after such that needs to be true for that element to be in that set. That's all I have for today, and thanks for watching.